Okay, so hi everybody, and thanks for this kind invitation. I'm very pleased and honored to be a discussant of the DeFinetti lecture, and in particular of Phil's talk. Actually, when I read the title, I was a bit scared because I thought that putting together Bruno DeFinetti's name next to objectivity was a sort of oxymoron, so I might have not been able to discuss this. I try to put up some ideas on around Phil's intriguing arguments. First of all, the starting point of Phil's talk is somehow the complementarity between the definition of a subjective probability and its evaluation. So basically, the way you define probability in DeFinetti's approach is to use a betting scheme. Okay, so as Phil was saying, you take a finite number of events, E1, E2, En, and you bet stakes C1, C2, Cn, and you have to ensure that the function P on a subset on the class on omega is such that you never have sure losses or sure wins. Okay, so this is a very general definition that gives you a lot of freedom. Okay, which doesn't mean anything goes, as Phil was feared about, but it means that, for instance, you don't need a specific structure of a class of subsets of omega on which define P. So it does not need to be a sigma algebra, for example. Anything, you have a huge freedom. Of course, there is a price you pay for it, okay? But it's very intuitive here. Of course, from this definition, you would like to somehow deduce an operational rule for assessing probabilities, and DeFinetti has been working on this for quite a while in terms of scoring rules. So how to relate probability evaluation with observed evidence. And it's really important to emphasize what Phil has said. So we are not trying to discover a true distribution given by nature. We are trying to confront ourselves with the experimental outcomes. And that's how DeFinetti came into working on scoring rules for measuring probability. So two examples we have seen with Phil are the Breyer scoring rule and the Good scoring rule. This is the binary case where we basically focus on events. Okay, so we confront P of E, our probability assessment, with the indicator function of the event E. If you quote a distribution which is different from your objective probability assessment of the event E, you get a penalization which, as Phil has shown, is either the squared form or the KL divergence. Of course, here honesty or properness corresponds to the case that when P bar is equal to P, so the quoted probability equals to the actual one, these penalizations are equal to 0. And this has been extensively applied by DeFinetti in some experiments on football games with 3 outcomes, as Phil was saying, at the University of Rome for the 1960 Italian Championship. But what I was very interested in the talk relates about prediction and the asymptotic results that have been shown. So suppose we define a sequence of predictive rules associated, for example, to an exchangeable sequence here. So I denote by pi n of A the probability that n plus 1th outcome equals A given x1, x2, xn. And suppose we take on a first n observations from 1 to n, those predictions that are far apart from some number between 0 and 1 by less than delta, okay? And with Kn, I denote its cardinality. So, and Kn is such that it diverges to plus infinity. And let me define then the average predictive distribution as pi bar n and the predictive distribution on those subset by rho bar n. And the Breyer scoring rule can be decomposed into these 2 components that Phil has named calibration and refinement, okay, which we would like to be as small as possible. And calibration amounts to considering the predictive probabilities on this subset of the first n observations to be as close as possible to the actual outcome. So we need to have these asymptotic equivalence with probability 1. And more importantly, if you do have two predictive rules, so two forecasts that are calibrated in this sense with respect to the same set of outcomes, then you have this convergence of, on this set A, still with probability 1, which really reminds me of the idea somehow of merging of opinions you have in this very nice paper by Blackwell and Dubins in 1962, even though they were looking at differences of predictive distributions with respect to the total variation norm, but it reminded me a lot of this. Of course, an interesting thing to note is that this particular event on which we would like to have probability 1 is actually a not observable event, okay? It's a limiting event. It's something we cannot observe. And of course, if we work with countable additive probabilities, this is not a problem because we have a unique extension that allows us to examine this in a neat way. But what happens if we work with finitely additive probabilities? What happens in this case? In this case, strange things can happen, of course, because you cannot phrase limit theorems in the same way you do with countable additive probabilities, and you need to work with finite eddy sets. Sorry for the repetition here. So you need to work with events that depend only on finitely many coordinates of your observation process. There are some papers in this direction, for instance, Berti, Regazzini, and Rigo on forecast. Regazzini and Zanoni, who gave some law of large numbers for finitely additive probabilities using this approach, and a paper of mine, a very old one when I was still very young, on the law of the iterated logarithm, where everything is based on this idea, working on observable events through these finite eddy sets. Of course, if you actually work with a countable additive probability, which is coherent in the sense of DeFinetti, then you have the classical results, both in probability and for this well-calibrated setting. Another question I would like to address is the problem of working with more than one sample. The examples that have been displayed in the lecture relate to the case where we have an exchangeable sequence of events or of random variables. What happens if we have different samples that are not exchangeable one across the other? So let's consider again the example with the schools where we have two schools. And suppose Thomas is in school 1. We want to predict the outcome of his stats exam. Would it depend on his own performance or on the performance of students just on the first school he belongs to? Or should it more reasonably depend also on the performance of students from both schools 1 and 2? So we have two groups of observations in this case, x1, x2, xn, y1, y2, ym. And we determine some predictive rules that correspond to the first sequence and to the second sequence, and which in line of principle could depend on all the observations. A simple way to do this is to think of the usual Bayesian approach of setting a prior on a parameter space capital theta, and to think of partially exchangeable data, for example, where you have the first sample being exchangeable within, and similarly for the second sample, but you don't have exchangeability across the two samples, and pi acts as a prior on the space theta squared. So you can get predictive rules for both the first sequence and the second sequence, depending on both sets of observations, x and y. And you can have extreme cases, you see, the case where pi is concentrated on the diagonal, theta 1 and theta 2, or where you have conditional independence. So there is no interaction between the two samples. So the prediction of xn plus 1 depends only on x and not on y. And the same for the prediction of ym plus 1. So Of course, more intriguing is the case where theta has infinite dimension, where you are in the Bayesian non-parametrics realm, and I've been working on this a bit. And in this case, you can determine some forms of these predictive distributions F1 and Fn. And a nice intriguing case is where these predictive distributions can be seen as convex linear combinations of these two extreme cases, the full exchangeability and the unconditional independence. And I have some work with some co-authors of mine on this subject. So, I mean, it would be interesting to see whether this approach to scoring rules can be somehow extended to this more general case. If there is a way of formulating the notion of calibrated forecast, I actually have no idea, but it would be very interesting. And in particular, as for the problem of merging of opinions, what is not actually merging of opinions, but reminiscent of it, can we compare the two extreme situations where we have full exchangeability versus unconditional independence? So could I expect something really paradoxical in the sense that the prediction made by someone who thinks that everything is exchangeable merges with the opinion of someone who thinks that everything is unconditionally independent? That would be really surprising for me. And that's all I wanted to say, and I want to thank again Phil for his wonderful talk. Thanks.